If you've ever found yourself amazed by ChatGPT or used Copilot to write code, or even just played around with an AI image generator, well, you've been using tech that all started right here. It all comes back to this one single research paper from 2017. And the title? Oh man, the title made this incredibly bold claim. Attention is all you need. So, in this explainer, we're going to unpack exactly what that means, why it was just so revolutionary, and how this one single idea became the backbone of pretty much all of modern AI. All right, let's get into it.
Okay, so to really get the breakthrough, you have to understand the problem they were up against. For years and years, AI models basically, well, they read like we do, one word at a time from left to right. But imagine this. What if an AI could look at an entire sentence, not word by word, but all at once, like instantly seeing how every single word relates to every other word? What kind of power would that unlock? Seriously, that one question, that's the key to this whole thing. All right, here's the game plan for today. We'll kick things off with the revolutionary idea itself. Then we'll tackle the problem it solved, what I'm calling the tyranny of sequence. After that, we'll dive deep into the transformer architecture, check out its mind-blowing results, look at its legacy, and finish up with the most important takeaways for you. Okay, let's jump in to section 1, a revolutionary idea. And look, this wasn't just some small tweak or a minor improvement on an old model. No way. The authors came along and proposed a completely new way of thinking about how machines process language. They basically took the old rulebook and just threw it out the window. This quote right here from the paper's abstract, this is the heart of the whole revolution. You have to understand, for years, the absolute gold standard for this kind of stuff was something called recurrence, RNNs. And these authors just came in and said, yeah, let's just get rid of them entirely. Instead, they built this brand new thing, the transformer, based only on a concept called an attention mechanism. It was a huge, huge gamble. So to really appreciate just how bold that gamble was, we need to talk about the problem they were trying to solve. And that brings us right to section 2, the tyranny of sequence. So the big players on the block at the time were these things called recurrent neural networks, or RNNs for short. And just like it says here, they process everything one piece at a time. I mean, think about it like a line of dominoes. To get to that 10th domino, you absolutely have to knock over the first 9 in order. There's no skipping ahead. And that right there was the fundamental bottleneck. It's inherently sequential, which means you can't really parallelize the work. This made training on long sentences or massive data sets just painfully slow. And this slide, this is from table 1 in the paper, and it just perfectly shows the solution. Look on the left, with the old recurrent layers. The number of steps you have to take, your sequential operations, it's O of n. That just means it grows 1 for 1 with the length of the sentence. Longer sentence, more steps. Simple. But now, look at self-attention on the right. It's O of 1. Constant time. It literally doesn't matter if the sentence is 10 words or 1,000 words long. The number of sequential steps is 1. It can look at everything at once. This is the secret sauce that unlocks massive parallelization on modern GPUs. It's the difference between reading a book one tedious word at a time and just absorbing the entire page in a single glance. Which brings us perfectly to section 3. Attention is all you need. Okay, so we've tossed out the old way, we've gotten rid of recurrence. So what did they replace it with? Let's crack open the transformer and take a look inside. So the transformer has 2 main halves. First up, you've got the encoder. Its one and only job is to read the input sentence and build a really, really rich understanding of it. To do this, it stacks 6 identical layers on top of each other. Now, each of these layers has 2 main components. You've got the multi-headed tension, that's the magic sauce we're going to get to in a sec, and then a pretty standard feed-forward network to chew on the results. Oh, and remember how we threw out the whole idea of sequence? Well, to make sure the model still knows which word comes first, second, third, they just add some information about the position of each word right at the very beginning. All right, the other half is the decoder. Its job is to actually generate the output, the translated sentence. It's built a lot like the encoder, but with a couple of really clever twists. First, its own self-attention is masked. That's just a fancy way of saying it's not allowed to peek ahead at the words it hasn't generated yet. No cheating. And second, it has this extra attention layer that is constantly looking back at what the encoder figured out. This is the critical link, right? It's how the decoder makes sure the French translation is actually, a translation of the original English sentence. So what is this attention thing anyway? The paper calls it scaled dot product attention, which sounds complicated, but the intuition behind it is actually pretty simple. For every single word, the model generates 3 little vectors: a query, a key, and a value. Think of it like this. Let's say we have the sentence, "The cat sat on the mat." For the word sat, the model might generate a query that's basically asking, hey, who or what did the sitting? It then takes that query and compares it to the key of every other word in the sentence. And of course, the key for the word cat is going to be a super strong match. So the model then pulls the associated value from cat, which essentially gives it the context it needs. That's it. That's how words talk to each other and figure out who is relevant to whom.
And here it is, the math that makes it all happen. It looks a little intimidating, but let's break it down. You take your queries and your keys and you multiply them together to get a raw score of how much they match. Then comes this really, really important step. You scale it down. You divide by the square root of d sub k, the dimension of your key vectors. Why? Well, the authors figured out that without this step, the scores could get way too big and the gradients would just vanish during training. It basically stops the whole learning process cold. So after scaling, you run it through a softmax. That just turns all those scores into nice, clean percentages or weights. And finally, you multiply those weights by the values. And that's it. That little equation, that is the engine of the entire transformer.
But they didn't stop there. They took it another step further with something called multi-head attention. The idea is, instead of just doing this whole query key value dance once, why not do it multiple times in parallel? In the paper, they use 8 heads. You can think of each head as having its own little perspective on the sentence. So maybe one head gets really good at tracking subjects and verbs. Another head might focus on pronoun relationships. A third could track, a sense of time or tense. By running all these in parallel and then combining the results, the model gets a much, much richer and more nuanced understanding of the language. It's like having a committee of experts looking at the sentence instead of just one person. So, okay, we've got this beautiful, elegant, highly parallel new architecture. It's great on paper, but the million-dollar question is, did it actually work? Was it any good? Let's find out. Time for section 4. Putting transformers to the test.
Did it work? Oh, it didn't just work. It absolutely shattered the state of the art. On the standard benchmark for English to German translation, it hit a blue score of 28.4. Now, that number might not mean much to you, but let me put it in perspective. The previous best score, achieved by a complex mess of different models all working together, was around 26.3. Gaining over 2 full blue points on this task, that wasn't just a step forward. That was a giant leap. It was unheard of.
But wait, because here's the real kicker. Take a look at this table. The transformer wasn't just more accurate, it was insanely more efficient. It got that brand new state-of-the-art score using less than a third of the computational power, the flops, of the previous best model. Let that sink in. Better results for a fraction of the cost. This was it. This was the ultimate proof that their big gamble on parallelization was the future. And that raw efficiency, it translated directly into game-changing speed. We're talking about training jobs that used to take weeks on huge clusters of GPUs, now being done in 3.5 days for the big model, or get this, just 12 hours for the base model. That didn't just break records, it completely changed the game for researchers. It broke down the barriers and made cutting-edge AI accessible like never before. And this all leads us right into Section 5, the legacy of the transformer. Because with results like these, the architecture didn't just influence the field, it completely and totally took over. It set the entire world of AI on a brand new path. I mean, think about it. Pretty much every major AI breakthrough since 2017 is built on this foundation. You know GPT? The T stands for transformer. code completion tools that finish your sentences? Yep, that's a transformer. Those incredible models that generate images from a text prompt, they use a transformer to understand what you're asking for. It even jumped beyond language to things like predicting how proteins will fold. This one architecture became this universal, all-purpose tool for finding patterns in pretty much any kind of data. Okay, let's bring it all home. Section 6, your key takeaways. If you walk away from this explainer remembering just a couple of things from this paper, make it these.
All right, first big breakthrough. Parallelism beats recurrence hands down. The paper proved that ditching that one word at a time process leads to way faster training and better results. Second breakthrough, self-attention is all the engine you need. All that complicated machinery from the old models, turns out it wasn't necessary. This one simple, elegant mechanism was powerful enough to do the job. And finally, the third breakthrough, it gave us a super flexible, general-purpose architecture, the encoder-decoder structure that has basically become the standard blueprint for AI ever since.
So the authors of this paper looked at a fundamental assumption everyone held, that you needed recurrence to understand sequences, and they challenged it. And that one challenge literally changed the world. So it leaves us with one final question to chew on. What's the fundamental assumption we all hold about AI right now that's just waiting for the next revolutionary paper to come along and prove it wrong?